Okay, I think we can start. So, good morning. Welcome to the fourth lecture already of this series of 5 lectures. So in the first lecture, I gave a bit of an overview of uncertainty in computational geometry. In the second one, we saw how to compute bounds on measures. In the third one, I talked about this preprocessing paradigm. Now I want to go back to the bounds on measures, but now in a probabilistic setting. So, so far, I've only said uncertainty regions are regions where we know there is a point, but we didn't assume anything about probability distributions. But of course, uncertainty is very much related to probability theory and statistics. So today we'll take a more probabilistic point of view to uncertainty and see what we can do in such a case. Okay. Well, I have a pointer. Yeah, I just tested it before the lecture and it worked. And of course, now it doesn't anymore. No? Okay, I will use this pointer. Maybe. I will continue with this one for now. Oh, it's working? What did you do? You pressed the magic button?
Yeah, maybe. Just this one and that.
Yeah, I know. That's what I tried.
No, maybe with the other hand.
Okay. Maybe yes. It's sensitive to that. Okay. Sorry for this little technical intermezzo. So, just to recap, this is the slide from the first presentation, just to bring you on the same page. Probability and independence is one aspect of uncertainty. Maybe we don't just want to say I have an uncertain point with some possible set of locations, but maybe I want to assign probabilities to those locations. So, for example, I may have a point which has 2 possible locations, each with probability 1/2. Or maybe the probabilities are different, or maybe I have more points. As long as these probabilities sum to 1, it's a valid random variable. I may have a continuous distribution of my uncertainty. I may have a uniform distribution that's defined on a region. I may have more than 1 point, like n points. And again, they may be discrete uncertain points, like here. So I've changed my points to have little different shapes, because I think it was maybe not so visible which color the points had before. So hopefully this works better. And again, so the question, of course, is, are these probabilities independent? And probably they are not in most applications. But if we have to model this dependence, things get much harder. So for today, I'm just going to assume all my random variables are always independent. Okay. All right. So the first question is, if we're dealing with these probability distributions, maybe the most natural setting is that we have a continuous distribution, like a Gaussian distribution. For example, if I measure my point with GPS, then I get some location, and probably the point is close to it, but maybe it's further away, and a reasonable model for this is a continuous probability distribution. However, these things are very hard to calculate with, so the first thing I'm going to do is approximate my continuous distributions by discrete distributions. Okay? So how can we do this? Well, there's a very useful concept for this, which is called quantization, epsilon quantization. And I first talk about the one-dimensional version of this to get the concept across. So suppose we have an uncertain point in one-dimensional space, and we have some continuous probability distribution on this point. So we have our space, it's a line, and we have some distribution that says, well, for every point of the line, there's some likeliness that the point is actually there, but it's a continuous distribution. So we have this function, and the area under the function has to equal 1, right? We know this from basic probability theory. So how do we approximate such a thing by a point set? It's a bit hard to formalize because points are discrete, so the probability of any point being the real point here in this continuous case is, of course, 0. So how can we still do a useful approximation? Well, we can do it by looking at the cumulative version of the distribution. So if I look at the cumulative distribution function, then this is the integral. So the value of this green function is the integral of the yellow function up to this x coordinate. And this green function is some xy monotone function that's 0 in minus infinity and 1 in plus infinity. And this one is much easier to approximate, or at least more insightful. So we can approximate this green function by some sort of step function like this. So here I'm making a function with steps of height epsilon, or rather I'm making sure that the height between the green function and the red function is always at most epsilon, so I actually have steps of height 2 epsilon. And now this step function we can project back down to the line like this, and now I have a point set. And this point set is called the epsilon quantization of this distribution, and we can say things like any region that contains a certain number of points has a probability within an epsilon error of the probability that the region contains a point in the continuous case. So it's a useful way to approximate this continuous distribution. And this concept of epsilon quantization we can also generalize to higher dimensions. So in 2 dimensions it looks something like this. We have a 2-dimensional space, so I have an x and y axis here, but I'm drawing a 3-dimensional picture, so it's like a projected version. So we have some 2-dimensional probability distribution. It's some surface that lives in 3-dimensional space. And we can again take a cumulative version of this. Now it's cumulative in 2 dimensions. For this we can build some approximation, and now we project down the sum of the points of this approximation. So the way you have to interpret this is for any point in 2-dimensional space, the height of this step function is the number of points that's contained in the quarter plane that's centered at such a point. So for example, you have these, I guess it's the quarter plane this direction. So here I have a vertex on my step function, which is defined by these 2 points, because if I am here, then the quarter plane contains 2 points. If I go down this step, then it's because I contain just 1 point, and on this side I also contain 1 point, and here it contains 0 points. Okay, so that's just how you have to interpret this step function. And again, it's defined by a set of points in the plane, and we wanted to approximate this function by being within height epsilon difference everywhere. And again, this is possible, and this point set is now the 2-dimensional epsilon quantization of our distribution. Okay, so this is useful, and we can use these for many applications, not for all of them. So at the end I will say that there are some applications where this doesn't work, like visibility. But for many applications, it does work. For example, when you want to compute some basic measure, like the diameter or the width of the point set, then we can use such a quantization as an approximation of a continuous distribution. Okay, is this clear? Because for now I'm going to forget about anything continuous and just talk about discrete distributions. All right? Okay. So, output distributions. Suppose we have a measure that computes a value on a set of points in the plane, like before. Okay, mu is some function. It takes a point set. It produces a real number. And before we said, well, if the points are uncertain, then we can compute an interval of possible values. But if we actually have a probability distribution for every point, then we can do more. We can actually compute the probability distribution of this whole measure, right? So P is a set of probabilistic points, so uncertain points with a probability distribution. Then mu of P also has a probability distribution. We can just see it as a random variable. Okay, so if each point has k possible locations, then there are k to the n possible point sets, and each of them has a certain probability of being the real answer. So this gives us a probability distribution over the output value. Okay, question is, well, this is of course an exponential number. Can we still do something in polynomial time? Can we compute this distribution, describe it, approximate it? What can we do if we only want to spend polynomial time? Okay. And the answer is it really depends on the measure, and it's not so obvious at first sight when this is possible and when this is not possible. So I'm going to talk about two different measures, and in one case I'm going to show you that you can compute this distribution and describe it in polynomial time, and in the other case it's NP-hard. The two measures are smallest enclosing circle and diameter. Okay, so two measures that look very similar at first sight. Smallest enclosing circle is one I haven't talked about before yet, so I'll just quickly define it. If we're given a set of points P, so this is a precise set of points in the plane, then the smallest enclosing circle is the smallest circle that encloses the points. Okay, it's a pretty clear definition, I think. Okay, we take a circle around the points and we shrink it until it cannot be shrunk further. So it's a measure somehow of the extent of the point set. And we can make some observations about it. So one of them is the concept of a basis. So I say the basis of my smallest enclosing circle is the set of points that actually lie on the smallest enclosing circle. Okay, so you can see there are 3 points that define the smallest enclosing circle, or equivalently, the basis is the smallest subset of my points which has the same smallest enclosing circle as the whole point set. Okay, if I take just these 3 points and I compute the smallest enclosing circle of them, then I get the same circle as for the whole point set. Okay, so this is what I call the basis of this measure. And we can observe that the smallest enclosing circle always has a basis of either 2 or 3 points, or 1 point if my set is only 1 point, but that's maybe a not such an interesting case. If my point set has at least 2 points, then it's always 2 or 3 points. Okay, so in this case it's 3, and here in this case it consists of 2 points, and these are the only possible cases. Okay, so now let's look at the smallest enclosing circle in the uncertain case. So I have again a set of points. Now they are probabilistic points, and I want to compute the distribution of possible values of the smallest enclosing circle. Okay, so here's my point set. I have 3 blue points, 3 yellow points, and 3 red points. What are the possible smallest enclosing circles? Well, obviously, a basis consists of at most 3 points. So if I have n points, then I have to choose 3 of them to form my basis. So that gives n to the 3rd possible probabilistic points that define the basis. And then each of these points has k possible locations. So I get k to the 3 possible instances of those 3 probabilistic points. So in total I get n to the 3 times k to the 3 possible bases. For example, here is one. I could have this smallest enclosing circle. Or here's one. I could have these 3 points. Or I could have these 2 points. Or these 2 points. And so there's only n to the 3 times k to the 3 possible bases. But of course, there are k to the n possible point sets. So there must be multiple point sets that have the same basis. And this makes sense. So, for example, if I take the basis consisting of this blue point and this red point, then there are 3 different sets which have this basis, namely this set. If I take this set of 3 points, then my basis is this blue point and this red point. But this set also has the same basis. Okay, it also has this blue and this red point, and this set also has the same basis. So there are multiple sets with the same basis. Okay, kind of obvious. So now, if we just count the number of supports of each basis, then we get our probability distribution, right? We have a set of n to the third k to the third possible bases. We count how many supports they all have, and we draw some sort of figure here. So here I have my possible values d of the, let's say, the size of my smallest enclosing circle. And for each value, for each basis, I have a different value of d. And I count how many actual point sets support this basis. And that's the number of steps I go up in this function. So the smallest distance here, that corresponds to this smallest circle here. But I have only one support for this basis, so I only go up by 1 step in this function. And then I have another one with 1 and some other small steps here. And there's also some steps where we go up by more than 1 because there are multiple supports for such a basis. So I can draw this function. And this is exactly the cumulative probability distribution of my measure. If I scale this down so that 27 becomes 1, so I divide by k to the n. Okay, so this is the thing that we want to compute, and we can already see here that the complexity of this function is not too bad. It's only there are only n to the third, k to the third different values of d where I change the probability. So the complexity of this step function is at most n to the 3, k to the 3. So it's not exponential. But then still, of course, we have the question how to compute it. And it turns out that we can compute it fairly easily. So how do we count the number of supports for one basis? Well, just look at the basis and look at the numbers of points inside the circle and multiply them. Okay, so maybe I have a situation like this. I have 4 uncertain points. Each of them has 4 possible values. I have a basis that consists of 2 of these points. And I want to know how many supports there are for this basis. Well, we can see for the red point, if the point set has to have this basis, then I have to pick this red point. I don't have any choice. For the yellow point, I should pick either this point or this point, because if I pick one outside the circle, then it won't have this basis. For the green point, I can pick this or this point, but not this one. And for the blue point, I have to pick this point, because it's actually on the basis. Okay, so I have these possible choices for my points. 1 choice for red, 2 for yellow, 3 for green, 1 for blue. 1 times 2 times 3 times 1 equals 6. So I have 6 possible supports for this basis. Okay, so it's just a matter of counting the number of points inside the circle. And then if we do this cleverly while we are summing over all possible bases, then we can actually compute this in just linear overhead per basis. So the distribution has complexity nk to the third, and we can compute it in nk to the 4th time. So this is polynomial. Okay? Any questions about this part? Okay, so then let's move on to another measure, which on first sight looks very similar to the smallest enclosing circle, the diameter. So the smallest enclosing circle is a way to measure the size of a point set, and the diameter is a way to measure the size of a point set. And the definition is kind of similar, maybe. It looks close to it. So for diameter, the definition is just take a set of points and try all the distances between 2 points and pick the largest one. So this is the diameter of this point set. And now we wanted to compute the distribution of possible values of this diameter. So we can just try to take the same approach, right? So the basis of a diameter is the set of points that define the diameter, but since the diameter is defined as the distance between 2 points, obviously the basis consists of those 2 points. Okay, it's fairly clear. So only 2 points, which means there's only nk. So this is for the exact case. So now if we go to the probabilistic points, can we just do the same thing? Well, we look at this probabilistic point set. The basis is defined somehow by 2 points of different colors. So there's nk squared possible values. So the step function again will have polynomial complexity. But now if we try to count the number of supports of one basis, we run into some problem. So suppose I want to look at this basis and I want to count how many point sets have these 2 points that define their diameter. Okay, so we can try to do the same thing and say, well, I can look at least at this shape. So if any point lies outside this loon shape, then it will be further than this distance from at least one of the points, right? If a point is here, then it's too far from this blue point. If a point is out here, then it's too far from this red point. So anything out there we cannot use. But anything inside this loon could be in a point set that has this diameter. However, not every combination of points inside this loon shape has this diameter, and that's a problem. Okay, so I can look at the set of points which could contribute to a set which has this basis. And so I see for green, I could choose this point or this point, but not this one. For yellow, I can pick this one or this one, but not this one. And blue and red, of course, they are defined because they define the basis. But now if I look at every possible combination of a yellow and a green point, then I see for this set here, I'm okay. So for this set of 4 points, this is indeed the diameter. And for this set, I'm also okay. So for this set of 4 points, this is the diameter. And for this set, also, this is the diameter. However, for this set, this is the diameter. So if I would just multiply those numbers, I would be overcounting. I would be counting some point set which actually has a different diameter, and that messes up my distribution. So I cannot just do the same counting approach. And it turns out that this exact problem here of counting how many supports there are for a given basis is what makes the problem hard. So we cannot just multiply the numbers of points to count the supports of one basis. And in fact, it turns out that counting the number of supports of a basis is sharp P hard. Does everybody know what sharp P hard is? Yes? Yes? Okay. So it's like NP hard, but maybe even harder. So why is this sharp P hard? Well, let's do a little hardness proof again. Diameter, we're going to make a reduction, and the problem I'm going to reduce from is this sharp 2 set. So this problem is counting the number of variable assignments which satisfy a given 2 set formula. So 2 set formula is a set formula where every clause has exactly 2 literals. But I'm going to reduce from a special version, which we call sharp 2L2 set. So it's 2 sets, but now every literal appears in at most 2 clauses. Okay, so not every variable, but every literal. So if I have a variable x, then x can appear in exactly 2 clauses, or 1. And not x can also appear in 2 clauses, but not in more than 2. Okay? And so we get some set of clauses like this. So here I have x1 or not x2, and not x1 or x3. And we can see x1 appears here and nowhere else. And not x1 appears here and here. So it's at most twice, and you can verify for every literal that it appears at most twice. And I am going to claim that this is still a sharp p-hard problem. The proof is not so hard. You just, if you don't have this situation, you can introduce some dummy variables to make it have this form. I'm not going to go through those details. Just assume that this is sharp p-hard, and now reduce diameter from this problem. Okay, so one observation we can make about an instance of 2L2 set is if I look at the graph, which has one vertex for every possible literal and an edge for every clause, so I have a clause, an edge between x1 and not x2, because there's a clause that has both of them. So I can draw this graph. So here are all my literals. I have x1 and not x1, x2 and not x2. And I just draw in these edges for the clauses that were on the previous slide. Okay, so I have, this is my clause x1 or not x2. And well, for every clause I have one edge. Then the observation is that the graph that I just drew is a path, or a set of paths. Okay, why is this? Well, since every literal appears in at most two clauses, it has at most two edges, and a graph in which every vertex has degree at most 2 is a path, or a cycle actually. So it could also be, there could be cycles here. Okay, so I have this graph which is a set of paths or cycles, and now I want to make an instance of my probabilistic diameter counting problem which solves this instance. Okay, so for this, the idea is that we can embed this graph. So for every vertex, I'm going to pick a point in the plane, so it's like a graph drawing problem, in such a way that if there's an edge between my 2 points, their distance is greater than d. And if there's not an edge between my 2 points, the distance is smaller than d. Okay, so this means that if I want to solve my my diameter counting problem, I'm looking for assignments of truth to the variables such that for every edge, only one of those two clauses, literals, appears in my point set, which corresponds exactly to not choosing this point. Okay, so one way to do it is to draw this big circle. So I spread out a set of points on the circle such that this distance is just larger than d, and all of these other distances are smaller than d. And so I have my clause here between x1 and not x2. So if I pick x1 in my point set, then I cannot also pick not x2 in my point set if I want to have a point set of diameter less than d. So you may think, well, that's not exactly what a clause is. That's true, but it's actually the inverse of a clause. So in other words, if I now reverse the truth values of all my literals, then it says that I have to either make x1 false or x2 true to satisfy this constraint that these 2 points are not at distance d from each other. Okay? Is that idea sort of clear? So each variable x1 up to x5 corresponds to exactly one probabilistic point with 2 possible locations. And well, this construction shows that if I want to count the number of possible point sets which have a diameter smaller than any given number d, then this counting problem is sharp p hard. So in particular, if I want to draw my cumulative distribution function and I want to know the height of this function at any given point, computing this height is sharp p hard. So I cannot efficiently compute this distribution function, even though it has only polynomial complexity. Any questions about this part? Okay, if not, then let's continue with the next topic. Okay, so we've seen that there's two measures which are somehow very similar intuitively, largest enclosing circle and diameter. In one case, we can efficiently compute this probability distribution. In the other case, it's hard. So it's somehow a very strange property of this kind of analysis, maybe. But you may wonder, okay, if such a problem is hard, can we still do something else that's useful? Can we still compute some aspect of this probability distribution that's interesting, or maybe some other way to interpret this uncertain point set that gives some useful information? And for this, I want to define the concept of shape inclusion probabilities. Okay, so a shape inclusion probability is the following. So again, consider a set of probabilistic points in the discrete model. So we have, or not in the discrete model. So in general, we can define this for any distributions. So these are supposed to be Gaussian distributions, right? So they have this bright spot in the middle, which has higher probability, and then they smooth out towards infinity. So I have a set of these uncertain points. And now I'm not just interested in some value on this set of points, but actually in a location as well. So suppose, again, I go back to the smallest enclosing circle. Okay, we know we can compute the distribution in polynomial time, but maybe I want to know not just the size of the smallest enclosing circle, but I want to know where the smallest enclosing circle is. Okay, so of course, there's an infinite number of possible smallest enclosing circles in this continuous case. So how can we visualize this output distribution of circles? Okay, so for this, we can define the shape inclusion probability, called the SIP. That should be a P. It's not a probability. Okay, so we want to compute this shape inclusion probability of all points. So what is it? The shape inclusion probability of a point in the plane is the probability that this point lies inside my shape. So if my shape is the smallest enclosing circle, then in this particular case, all the points inside this contour line here have a 90% chance of being inside my smallest enclosing circle. And the points here have a 10% chance, or at least 10% chance of being inside my smallest enclosing circle. Okay, so these contour lines are contour lines of a three-dimensional function, which assigns to every point in the plane the probability of that point being inside my shape. Okay, and that's what we call the shape inclusion probability. So now let's go back to the discrete case and see if we can compute this. So the SIP of the SEC, shape inclusion probability of the smallest enclosing circle, didn't fit on my slides, so I have to use abbreviations. Not even if I rotate it a little bit. So now consider a discrete probabilistic set of endpoints with k possible locations, like before. What is now the shape inclusion probability of any point in the plane? Okay, can we describe this exactly? Well, turns out we can. So we can consider the arrangement of all the possible circles, so all the possible bases of the smallest enclosing circle. So we get this arrangement here, right? So this might be the smallest enclosing circle of these 3 points. This circle might be the smallest enclosing one if these 3 points are there. And so for every possible basis defines one of these circles, and I just draw all of them on top of each other. And this divides the plane into these cells. Okay, so there's only k times n to the 6th cells, right? There's k times n to the 3rd possible basis, and they all intersect each other in a constant number of points. So the complexity of this arrangement is kn to the 6th. So in this small example here, where I have 3 points that each have 3 possible locations, I get 9 to the 6th. So it's less than 1 million cells, so it's a small constant. And we can just compute this arrangement exactly, and now for every cell in the arrangement, assign the shape inclusion probability. So in every cell, the shape inclusion probability is constant. No matter where I am in this cell, there's always the same set of circles that I'm contained in. We can count the supports for all of these circles, and this gives us the probability for this cell. Okay, so we can just compute this for all the cells, and then we have an exact representation of the shape inclusion probability of the whole plane. But maybe I want actually a picture like I had on the previous slide, where I just show some contour lines, because maybe this whole arrangement is too much information. So I can draw some contour lines in these arrangements of circles. So maybe I want the contour line where I am in at least 3 circles. So I can trace out like the 3 level from the outside in this arrangement, and this gives me a contour line. And this is exactly what we did on this previous slide. So this picture here that you see, it looks a little bit wobbly, and that's because this actually is a contour line in an arrangement of circles of an approximation of these continuous distributions. And of course, the smaller you choose epsilon, the more smooth these contour lines will look. Okay, so this is something we can compute exactly in polynomial time for the smallest enclosing circle, but, well, that's maybe not so strange, because for the smallest enclosing circle, we could also compute the output distribution exactly in polynomial time. But what about things for which we cannot compute the output probability? Well, it turns out that in some cases, we can still compute this distribution of shape inclusion probabilities exactly. So the example I want to give is convex hulls. So convex hull is another shape defined on a set of points. And if we want to do an output distribution on convex hulls, then we run into some problem again. If I want to do an output distribution on the convex hull of a set of probabilistic points, so I have my point set here, 4 points, which each have 3 locations, and I want to compute the convex hull, well, then a basis of the convex hull actually can consist of n points, because I might just have n points which lie in convex position, and all of them are on the basis. So I have actually k to the n possible basis, which means I can have k to the n different values of, say, the area of the convex hull. So if I want to compute a distribution of the area of my convex hull, then it just has exponential complexity. So in the case of diameter, it had polynomial complexity, but it was hard to compute. In the case of convex hull, the complexity is even already exponential. So there's really nothing we can do, right? We can have all of these different convex hulls. There's just exponential number of them. There's nothing we can do. Okay? And actually, even if we just want some specific values in this probability distribution, like you can say, okay, well, this distribution may have exponential complexity, but can we at least compute the basis which has the highest likelihood of being the real convex hull? So which convex hull is most likely, which one has the largest number of supports? This is actually already NP-hard, as was proven by Suri et al. So maybe this is not very visible, but this is Suri et al. 2013. So it's fairly recent. There's really nothing we can do about this output distribution of convex hulls if we want to have exact algorithms. However, it turns out the shape inclusion probability of the convex hull can be computed in polynomial time. So somehow it's a more informative measure, and it's also easier to compute. So for the SIP of the convex hull, we want to subdivide the plane into regions where the shape inclusion probability is constant. And it turns out that for this we need to take this arrangement of all possible bases. And even though the number of bases is exponential, this arrangement only has polynomial complexity. So we can just take the arrangement of all the lines defined by all pairs of points of different colors. Okay? So that's going to look something like this. Like this. Okay. So it's a pretty dense-looking arrangement, but still it only has nk to the fourth cells because there's only nk squared lines. And now we can see that if I draw any kind of convex hull between points of 4 different colors, it's going to be somewhere in this arrangement, which means that inside any cell in this arrangement, the shape inclusion probability is constant. Okay? And still there's a question, of course, how can I compute this probability within one of these cells? And it turns out that this is also possible in polynomial time. In fact, you can do this in n log n time for a given cell after you do some preprocessing. And this is a very recent result from 2015 by Agarwal et al. So it turns out that you can compute these probabilities efficiently, and therefore you can again compute this whole distribution of shape inclusion probabilities and maybe extract contour lines if you want in polynomial time. So even though for looking at the distribution of possible values of some measure of the convex hull, there's really nothing you can do. You can still compute these shape inclusion probabilities efficiently. Okay. Any questions about this part? Yes?
Your problem doesn't depend on the distribution, isn't it?
It doesn't depend on distribution.
Different distribution, you have the same result.
Yes, yes. So it's working for discrete probability distribution, but it is not necessary that the probabilities of each point are equal. We can have any assignment of probabilities to those points, yes, if this is what you mean.
All of the problem is solved.
Sorry?
All of the problem has the same manner.
Yes, so for any set of probabilities, you can do the same thing. It's just that instead of counting points, then you have to take the weights of the points into account as well, but this is no problem. It all works. Any other question about shape inclusion probability? Yes?
Once you have the answer, is it difficult if you add movement, for example, one time?
You add movement as in you want to locally update the situation? Sorry? So if you've computed this this arrangement, say, and you move one point a little bit, then there will be some changes, of course, in the arrangement, but only in the lines that involve this point. And if the movement is somehow local, then the number of cells that are going to change will be, I think, only quadratic and instead of n to the fourth. So I think in quadratic time you should be able to update this. Maybe if you don't need to actually update the actual shapes of the cells, but you just want to keep this combinatoric situation, you can do it faster. But then you get some sort of kinetic data structure problem where you need to know what is the next cell that's going to collapse in this arrangement if I move one point. Okay. Any other questions about this part? Then I want to briefly also talk about, so far I've only talked about this discrete probability distributions, and I said, well, if you have a continuous one, you can approximate it by a discrete point set using this epsilon quantization. But this doesn't work in every possible application. So I just want to briefly talk about visibility problems between probabilistic points. And we'll see here that if we use a point set to approximate a continuous distribution in a visibility problem, this may not give any guarantee on the approximation ratio or the quality of the computed result. And so we have to do something else. Okay, so why is this? Well, consider this very simple problem. So I just have two probabilistic points. So I don't have a whole set, I only have two of them. So here are my two probabilistic points with nice, smooth Gaussian distributions. And I just want to know the probability that these 2 points can see each other, that they're visible from each other. Okay, it's kind of a simple problem maybe. The probability is just 1. So let's make it a little more interesting and add some obstacles. So we have a set of n obstacles. The obstacles are maybe convex polygons in the plane. And now again I want to know the probability that this green point can see this purple point and they're not blocked by one of these obstacles. Okay, now suddenly it's not so easy anymore. The probability is not 1, it's something between 0 and 1. And how can we efficiently compute it? So one first idea you might have is, well, we have these continuous distributions. We know that we can approximate them by point sets. So let's just compute some epsilon quantization of this point distribution and one of this, and just count how many of these pairs of points can see each other, and it gives us an approximation of the probability of visibility, right? So let's try. What's the probability that they can see each other? Let's put some set of points here on the left. So this set of 5 points, say, is some epsilon quantization of this left uncertain point, and this set of 5 points is an epsilon quantization of this right uncertain point, and I try to see if some pair of points can see each other. Well, for these two, yes, they can just see each other, so that's fine. I look at some other pair. These two also can just see each other. And I just try this for all pairs, and it turns out, well, for every pair of points, there's a line that just misses all of these obstacles, and they can all see each other. So my conclusion is the probability that these 2 points can see each other is 1. Okay, so this intuitively doesn't really make sense because there's all these obstacles, so there must be some possible locations of the point where they cannot see each other. But if I chose if I was unlucky in my choice of a quantization, even though this set of points approximates this distribution within some error of epsilon, I still cannot guarantee that I capture the situation correctly because I don't know in advance where my obstacles are going to be. And it could just be that they happen to be in such a place that I don't block any of this finite set of visibility arrays that's defined by this two finite sets of points. But maybe for the same set of obstacles, I had chosen a different quantization on the left and the right, like this one. Maybe it's also a valid epsilon quantization. And now I try to see which pairs of points can see each other, and I try some point, and well, these 2 points cannot see each other because there's some obstacle in between. And these 2 points, turns out they also cannot see each other because there's some obstacles in between. And maybe I try all pairs of points, and there's only 3 pairs that can see each other. So these 2 can see each other, these 2 can see each other, and these 2 can see each other, but any other pair cannot see each other. So I say, well, I have 5 points on the left and 5 on the right. So I have 25 possible pairs. Only 3 of them can see each other. So the probability that these 2 points can see each other is 3 over 25. Okay, so it's a kind of different number than 1, which we computed before. So you can see that the answer to this question really depends on where my points happen to be, or maybe where my obstacles happen to be. And since I don't know this in advance, there is not really anything useful we can do with such a point approximation. Okay? So we have to come up with some different strategy to solve this kind of problem. And it turns out that what we can do is, if we have a smooth probability distribution, say a Gaussian, instead of approximating it by a set of points, we can approximate it by a set of regions, where we assume that on every region we have a uniform probability distribution. And this makes the problem a little bit easier than computing directly on the Gaussian distributions. It's, of course, harder than computing on points, but it's somewhere in between, and it turns out that for regions, we don't have this problem that we might miss the obstacles, and they're still simple enough that we can do some reasonably efficient computations. Okay, so how do we compute, how do we approximate a set of, how do we approximate a probabilistic point by a set of regions? Well, the idea is kind of similar to that of the quantizations, except that now I'm not computing points, but regions. So again, I have some distribution, and I'm first going to approximate it by a set of concentric disks. Okay, so I have some distribution here. I again have I compute some step function. This time I'm going to use steps of different heights, and I'm going to balance the areas between these regions here, or actually not the areas in this two-dimensional picture, but the volumes in the rings that these form in a three-dimensional picture. So these volumes will be all equal. And then I'm going to further approximate these rings by polygons. Okay, so I have a set of concentric rings, and now I draw some polygons in between those rings. And then in the end, I get a picture that looks something like this. So I have my two-dimensional Gaussian smooth distribution, and I approximated it by this set of polygons, which are somehow stacked on top of each other, and they form this three-dimensional step function. So it's like this layered cake of polygonal shapes. And I want to minimize the area that's in between those two shapes. So I don't want the area that's in this cake but outside of the yellow mountain to be too large, and I also don't want the area that's inside the mountain but outside the cake to be too large. So I want to minimize this total area, but I also want to minimize the complexity of my cakes. And you have to somehow balance these two, and the mathematics behind this is a bit more complicated than if I just want to use a point set. But it turns out that I can still approximate such a Gaussian distribution within error epsilon by using a set of order 1 over epsilon polygons, where each polygon has a complexity of order 1 over square root of epsilon. Okay? So there's some function of epsilon that gives us the complexity of the approximation. So it's no longer just complexity 1 over epsilon as it was in the case of point sets. Okay? So now I have this set of regions. So one of these polygons now is a region, and the probability distribution on this region is uniform with the height of the region as the value of the distribution. Okay, so this means that for a point in the center, my probability will be the sum of these two individual probabilities. And with this, if we go back to our feasibility problem, now I have two regions in my set of obstacles, and now I can actually guarantee that if I correctly compute the probability that a point in this region can see a point in this region, then I get an actual epsilon approximation of the probability that the original points can see each other. Question, of course, is then how do we compute whether two such points can see each other? And for this, we have to do some complicated computational geometry. So we can do this in n squared times m squared time. And I didn't put in the slides that show this construction, mainly because it was already 2 a.m. and I didn't feel like making more slides, but also because maybe I thought I wouldn't have enough time to go through them anyway. So sorry, there will not be any details. But we can do this in n squared, m squared time, and if you're interested in how to do it, we wrote a paper which has all the details. And then if I apply this back to the original result, we arrive at, so the final result here is given two Gaussian distributions and a set of obstacles in the plane, we can approximate the probability that 2 points can see each other within an additive error of epsilon in time 1 over epsilon to the third plus n squared over epsilon squared. So this is just combining this claim with the quality of the approximation that we saw before. But really the takeaway point for this last part, I think, is that point sets are not always sufficient to approximate distributions. In some cases, you have to resort to regions, but for regions, you can still obtain results. Yes? M. So one of them is the complexity of the regions, and the other is the complexity of the obstacles. But I forget which one is which. But it doesn't matter, because it's n squared, m squared. Okay. Okay, so yeah, complexity of the region times the complexity of the obstacles squared. Any other questions? So I think this is the end. Yeah, so it's my final question slide anyway, so thank you. Are there any questions about any of today's talk? If not, then I think we can have a break, and then I have another talk for you after the break.